CLI and a cross-platform IDE for C and C++. Download now.
So, welcome everyone. Today, I would like to talk about coroutines and C++. And in the age of AI, let me start, please, my presentation with an AI-generated image that kind of represents the somewhat broken relationship between coroutines and C++. So, C++ coroutine have been remarkably successful at staying completely invisible since 2020. They exist, they work, they are also standardized, and yet nobody has seen them in the wild. They were, back in the days, a very hot topic. Many developers, including me, were eager to learn and use them. But over time, this hype has cooled down. Not disappeared entirely, but definitely cooled down. And the reason is most likely that C++ coroutines are extremely low level. And to truly benefit from them, first, we have to understand quite a lot from the underlying mechanism. So that would take several hours and at least one whiteboard. So we are going to skip that. And instead, I would like to show you how to make this seemingly useless feature useful. So my name is Tamas Kovacs. I'm a C++ software developer. And at some point in my career, I decided to take on a challenge of turning the C++ coroutines from a pure language feature into something actually usable. And that's how tinycoro was born. So most of the examples you see today are based on this library. But the concepts that I'm trying to show themselves are not tinycoro specific. So they exist in most modern coroutine libraries. The principles are everywhere basically the same. I'm only using tinycoro simply because I know it inside out, and it makes me easier to demonstrate those ideas clearly. So today, another goal would be that I'm trying to share with you the lessons I learned throughout this journey. So, but now let's quickly get back to the basics and make a short recap. What is a coroutine in C++? So one of my colleagues said, a function with commitment issues, which is not far off, to be honest. When we say that the coroutine is a generalization of a function, what do we actually mean? Think about a normal function first. So a regular function starts running, executes from top to bottom, and then simply returns. And that's it. The one single entry point and one single exit point, no pause in between. A coroutine is a bit more than that. A coroutine can suspend and resume the execution. That means it can pause in the middle of the work, return control to the caller, and later continue the execution where it left off, with all his local states and local variables. It can be switched between different threads, so you can suspend a coroutine on one thread and resume on another one. And coroutines doesn't have to run all the way down. So with a normal function, once you started it, you are basically committed. It runs until the end, unless you are using goto or exceptions, or your entire program crashes. But it's mostly you are committed and it's gonna run until the end. But the coroutine is different. It's more like just a task that you are managing. So if you decide that you don't care about the result anymore, you can just simply stop it, cancel it, throw it away, it doesn't matter. So instead of being something that is must finish, it becomes something that we can control. And now let's visualize those behaviors quickly. First, we are going to take a look into a simple function call. On the right side, we have a simple function, adding a value and returning it. And that's our current execution flow. So execution leaves the caller and jumps into the function. Inside the function, we compute and return the result. Everything here is strictly linear, nothing unusual happens. But what about the coroutine function call? On the right side, we have now coroutine, and at the first glance, it looks almost the same. But look at the return type. Ooh, it's not an int anymore, it's a task int. And when we call this coroutine, we are not immediately getting the final result. We are getting a task that is an object that represents this computation. And what about the return statement? We are using co-return instead of the simple return. So if you have co-return, co-yield, or co-await in your function body, this is a very, very strong signal that you are dealing with a coroutine function. So, and if you take a look into the control flow, then surprisingly, nothing very special happens. Just like a simple function call, the caller starts the coroutine, reaches the co-return, executes everything, and giving back everything to the caller. So pretty much the same as a simple function call. But what is if we have a suspension point in our coroutine? And this is which is pretty interesting. Because if you take a look on the right side now, in the middle of the function, we have a co-await, a simple suspension point. So this looks almost the same, but we have now co-await in the middle of coroutine function body, and that changes everything. So the coroutine starts running, it computes the value, still everything simple, but then we hit this line here, and we co-await suspend always. We are suspending the task. So the execution will jump back to the caller. But here's the important part. The coroutine does not disappear. It does not return. It does not lose his state. Everything, including all the local variables, is preserved inside the coroutine frame, and later someone can simply just resume it. And when it resumes, it continues exactly where it left off from the co-await. And then we are getting back the final result. That's great. And this is how the control flow looks like. So caller starts the coroutine, we are reaching the suspension point, gets suspended. The caller decides at later point to resume the coroutine, and exactly where it left off, getting the final result and the end, and that's it. But what about parallel execution? We have on the right side the same coroutine, single suspension point in the middle of the coroutine body, stood suspend always. And if we take a look into the control flow, then we can see that we are starting this coroutine from thread 1, reaching the suspension point, and the coroutine suspends, and then comes thread 2 in the picture and decides to resume the coroutine. He can do it, and he can get also the result from this coroutine. What they cannot do is to resume the same coroutine at the same time, because this would lead to undefined behavior. But what about destroying the coroutine function? So I said that the coroutine function can be destroyed before completion. That means on the right side the same coroutine, and if you take a look into the control flow, you can see caller resuming the coroutine, starting it, reaching the suspension point, and later he decides to destroy it completely. The coroutine can be only destroyed in suspended state. And if a coroutine is destroyed before reaching completion, the usual stack unwinding happens and all the local objects are properly destroyed. So that's great. We are safe here. This could be, for example, handy, destroying in a case that if we want to cancel our coroutine. So now that we covered quickly the basics, let's make some concepts and naming clear. So you may notice different names in different ecosystems. C++ standard calls them coroutines, Boost, ASIO calls them awaitable, and some other libraries calls them tasks. This is not because they are fundamentally different. This is because we are C++ developers. Single concept, multiple names. Welcome to C++. So me personally, I prefer the name task over the others, and I also try to explain it why. So if we put them on the scale and comparing the task with the waitable, it quickly turns out that task is a much bigger thing than a waitable. The task is responsible for the lifetime of the coroutine. It manages the coroutine frame and the suspension behavior. In other words, this is some kind of controller, some kind of manager of a coroutine. On the other hand, a waitable is usually just a small temporary object used in a co-wait expression. Its main job is very, very simple. Decides whether to suspend, how to suspend, and how to resume a coroutine. So if we are comparing both those two things conceptually, the task is a manager, while the awaitable is just a suspension mechanism, nothing more. So you usually don't need to fully understand tasks. Tasks are typically provided by the libraries or frameworks, and they hide all the complexity. Awaitables, however, are different. As a user, you will very often interact with awaitables, and you might even write your own one. But what do we actually gain from these coroutines / awaitables / tasks? So first, the coroutine tasks are very easy to schedule, whether that's a concurrent or parallel execution, you name it, doesn't really matter. The suspension points give us the natural place for cancellation, which is extremely hard to achieve with completion callbacks. Error handling, we can also rely on the normal C++ exceptions instead of some weird error propagation chains back to the caller. And most importantly, coroutines preserve the stack state across suspensions. So therefore, asynchronous code can still look and behave like synchronous code, which is great. But enough slides and theory, and let's look at some code now. So our first task is we are going to have an event, and we want to wait on this event. So first, I'm going to show you the normal C++ solution, standard solution. Here is represented the event by a stud atomic. We have the corresponding notify function, and we have the wait here. This works for sure, is efficient, and is completely fine at the low level. The important thing to notice here is this blocking wait. So while the thread is waiting here, it cannot do any other useful work, which is bad. So if you want to scale this to many waiting tasks, you quickly need many threads for that. But what about the coroutine solution? Conceptually, nothing's changed. Let's imagine a perfect world that we have an event. And this event we can set with his member function simply. And this event is also co-waitable. So nothing has changed. We still have an event, we still notify it, and we still wait for it. But the important difference is in wait. So instead of blocking a thread, we co-wait the event. This does not block anything. The coroutine is suspended, and the underlying thread is free to do other work. So and if the event is set, the coroutine is resumed exactly where it left off, which is great. And the stack, everything is preserved. Fine. In the previous slide, waiting consumed the thread. Here, waiting only suspends a coroutine, and this makes a cheap operation. What about, let's mix a little bit. So we want to have an event. This is our goal, this is our task, but we also want to add a timeout for this event. So this is going to be a usual blocking solution, but we need to have a conditional variable for this now. With a flag, with mutex, with everything which belongs to this pattern. So we have a notify, and this is our wait function. As you can see, here we have wait for, We are passing the timeout, we need the lock, we need the predicate, a little bit boilerplate, but we all know that how this thing works. And still blocks the underlying thread. But what about the coroutine version? So we have the same event, nothing changed there. We have now soft lock. Okay, you don't need too much about soft lock. Soft lock is very simple. It's just a lightweight thread-safe timer that schedules and executes callbacks after a certain duration. That's it. Our notify is untouched, the same. And this is our wait function. And now look at this function. We are still waiting for the same event, but now we add the timeout without changing the event itself, which is great. So event wait, this is our original awaitable. This gives us the original awaitable, and the timeout await, this gives us another awaitable. What we are doing here is composing awaitables together. So each awaitable is just a small and focused on one single and simple responsibility. One represents a wait for an event and another represents a timeout. So by combining them together, we create new behavior. And this is exactly the reason why awaitables matter to users. But now let's see, what if we want to have an event which is a cancelable event? A standard C++ standard gives us tools for that. We need to use conditional variable any now because we need support for stop source. The notify is the same as before, and we have now here the wait. As you can see, we are co-waiting. This is our wait for the conditional variable, and if this returns false, we explicitly need to return from this function because we don't want to execute this line anymore. So that's great. Works, but the cancellation logic is tightly coupled in this code. But what about the coroutine version? So the intent of the code hasn't changed. We have an event. We have also stop source. Notify function is still the same. And this is our wait function now, wait coroutine function. What we have here, this is our original event wait, which gives us an awaitable. And now we have a cancelable awaitable, which wraps everything together. And by composing them, we make this wait cancelable without changing the event or the waiting logic itself. That's great. But cancellation is a very tricky topic. So if you think from a design point of view, is it a good thing to make every suspension point implicitly cancelable? Probably not. Let's say that you are in the middle of some transaction and you don't want to make them cancelable in the middle. So by the way, making cancellation implicitly everywhere removes the control from the user. So with explicit awaitables, cancellation becomes a conscious decision. So you have to think about it. Do I really want to make this this suspension point cancelable or not? And if you see it, if you take a look into syntactically, the cancelable makes the intent here very, very obvious. So this suspension point is cancelable, others are not. Isn't that great that awaitables can give us the freedom to decide whether cancellation is allowed or it isn't? But let's move on. Let's mix everything together, all combined in one place. We want to have an event which is cancelable and which has a timeout on the top. Standard C++ solution, conditional variable, stop source. We have the notify, and this is our wait function. We are going to use the wait for with the token and the timeout. And if this returns false, we still need to explicitly check if the soft source is requested, because in a case of a timeout, we also return false. So all combined in one place. But now let's take a look into the coroutine version. What we are trying to do is exactly the same thing. we have an event, we have now soft clock, and we have the stop source. We have our notify, which is pretty simple still. And this is our wait coroutine. What we have here, we are waiting on an event with both a timeout and a cancellation. So, but instead of encoding all that logic into one blocking wait, we build it by composing awaitables. What we have here is event wait, which gives us the original awaitable directly from the event. We are wrapping it cancelable and adding a timeout with timeout await. So what's great about this design that none of these components know about each other. So the event wait doesn't know anything about cancellation or timeout, and the timeout doesn't know anything about cancellation or event. But we don't have to stop here. We could re-implement all the synchronization primitives. The key point is, if we have to wait, we can use coroutines. But how to run coroutines tasks concurrently? On the right side, on the left side, we have a coroutine which prints two lines, start and done. And in the middle of this coroutine, we have a suspension point, and we are going to sleep for 1 second. So first switch could pop in our mind that something like this, that we are going to co-await this task. So in execute one, we co-await the task one after the other. That means task 2 only starts after task 1 has fully finished. This is not really helpful, and the output reflects pretty well that this is gonna take 2 seconds. So this is not really a concurrent execution. So if we want concurrency, we have to say it explicitly. In our execute second example, we are using all of await, which gives us an awaitable that represents wait until all of these tasks are complete. And if you see the total time, this is gonna take 1 second. So this is cool. We are going to have here a concurrent execution. On the other hand, this is for coroutine context. If you are in coroutine, you can co-await it and create all of await for that. But what if you are not in a coroutine context? What else you can do? So then you can use all of. The same idea also works outside of coroutines. All of starts the task concurrently and waits until they complete. But in that case, this is going to be a thread blocking wait. But anyway, if you want and if you decide and you have to do it like this, you can make it work outside of coroutines also. So now let's take a closer look and discover our new concepts, the combiners. So all of and all of await. Once you start running tasks concurrently, you need a way to coordinate them somehow. And this is where combiners like all of come in the picture. So all of expresses a very, very simple intent, start multiple tasks and wait until all of them are finished. The results of all of is basically a tuple of optionals. That means that each task can either produce a value or be absent, for example, because of some cancellation. If one of the tasks throws an exception, all of propagates the first exception to the caller. And basically having both together, all of and all of await is absolutely intentional. So one works, as I already said, for synchronous code, and the other works in a coroutine context. Then we have all any of and any of await. Those are the arrays. So instead of waiting for everything, we want to wait for the first task to complete. And as soon as the first task completes, the remaining tasks are cancelled. So in case of some return value there, we are using std tuple with std optionals. The exception propagation is the same. The first exception will be propagated to the caller. And basically that's it. What matters here is not the exact API, because I'm showing now how this is in tinycoro, but the underlying idea. So those structured combiners like this show up in all coroutine libraries. So now that we covered the combiners, let's get back to our previous event example. And let me show you what I was talking about. If as I said, this is a blocking wait for the first event. So this is going to be a traditional blocking model. We have a std atomic bool, and we call a flag wait on this, which blocks the operation system thread until we change the value. And this thread cannot do anything else. So after we set this event, we simply do some async work. That's fine. If we want multiple waits to happen concurrently, we need multiple threads for that. So 3 concurrent waits requires 3 OS threads. But let's think of it a little bit. What's happening under the hood? So we are using heavyweight operation system threads just to wait. Simply, those threads are simply parked by the kernel somewhere in a list. That's really the waste of the resource. But let me show you the real power of coroutines. What we have here pretty much the same structurally. 3 waits, then we are doing some async work, but something fundamental changed. We are not blocking here. So all 3 waits can exist concurrently at the same time on a single thread. That's great. So far we control the waiting, but what about APIs we don't control? So let's imagine we are working on a legacy codebase which relies heavily on completion callbacks. We have now async download. This is our completion callback. First parameter gets a URL, and the second one is the callback. This is going to be a very, very typical piece of legacy code now. We have a callback-based asynchronous API, but we want to expose it somehow as a synchronous-looking function. To do that, we need latch, we need result, with exception pointer. In line 7, we are starting the async download. The first parameter is the URL, the second is the completion callback. We are getting the data, we are validating the data in completion callback and saving in results. In case of an exception, because we are validating it in this may throw us what, we are saving the exception. And in line 19, we are waiting on a latch. And this is a thread blocking wait. After this latch is notified here by the completion callback, we can move on and continue with execution. In case of an exception, we rethrow it, or otherwise simply return the result. So this works, but it's if you imagine it in a larger scale, it's extremely hard to maintain and doesn't scale well at all. But what about an awaitable? Can we write our custom awaitable to solve this issue? So let's look at what really happens inside this download awaitable. First, we define some members, result, the exception, and the resume callback. So there are 3 mandatory functions which we need to define if we want to write our custom awaitable. The first one is await ready, which is in our case returned false and carries the meaning, please always suspend. This triggers await suspend, our next function, next magic function. And this is basically the bridge. This is the bridge between the callback word and the coroutine word. And this is where the interesting part really starts. So when the coroutine is suspense, we receive its handler, the parameter, we are putting in the pause, and we are getting back a resume callback. Something we can safely call later to notify the suspended coroutine. Great. After that, we have our completion callback, pretty much the same logic. We are validating the data. in case of an exception, we are saving this exception or saving the data in result. And in line 13, we are resuming, we are notifying the coroutine for resumption. In line 16, async download kicks off the actual asynchronous work. And now we return from await suspend. The coroutine is in a suspended state. The network operation is in flight, and we are just waiting for the completion callback to fire. Last but not least, we have await resume. If an exception occurred, we are rethrowing them, otherwise simply returning the result. That's it. This looks like a lot of code, but conceptually it's very, very simple. And from the caller perspective, this now behaves like a normal function call, but it is completely non-working. So, of course, if you want, you can make this download awaitable more generic and reusable. For example, by creating a constructor and by accepting the URL in the constructor, for example. But for me, I was pretty limited by the slides, so I decided not to make them so generic. So now there is one subtle but very important detail here. Inside the completion callback, we called resume. But what actually happens when we do that? First, it looks like kind of voodoo magic in the background now, I guess. But let's find out. So C++ standard, in C++ standard, nothing stops us from resuming the coroutine directly. So one coroutine can resume the other one. At first glance, this looks like a very flexible idea. But if this is allowed, you can easily end up with a resume chain, just like a linked list on the right side. So one task resumes the other and the other and the other, and they can never be cleaned up. So in extreme cases, this can lead to very long call stacks and even Stack Overflow. So with that in mind, we decided that we enforce a strict rule for tinycoro. So only the scheduler is allowed to resume suspended coroutines. This is nothing new. Other languages using the same principle, for example, Swift. But this design has, of course, advantages and disadvantages. On the positive side, it gives us full control over coroutine resumption, which makes feature like cancellation easier and very, very robust. On the downside, it introduces, of course, some performance overhead. But if we think from the design point of view, we learned already 3 different concepts, right? First one was the task, which describes what should run. Then we learned the awaitables, which describe when and how to suspend. And we have a scheduler, which decides when to run a task. So in tinycoro, we have the inline scheduler, which gives us concurrent execution, single-threaded. And we have a tinycoro scheduler, which provides us parallel execution with multiple workers. And this is a simple example. So all of the combiners, as a first parameter, you can if you want, you can decide you can give the scheduler as a parameter. They will accept it. So now that we covered how coroutines execute, let's talk about how they can communicate with each other. So coroutines are great building blocks for channels generally because of his nature to handle very well those back pressure situations. So let me show you this in an example. So this is going to be a single producer consumer example using with a buffer channel. A channel has a fixed capacity, in our case 4. So think of it, a channel as a thread-safe queue that coroutines can push to or prop from it without blocking a thread. So if the buffer in our producer version, we are producing the values. We are going to produce 10 values in this queue, pushing back 42 every time. And if the buffer is full, so we reach the count 4, push wait suspends the producer coroutine. On the other hand, if you have a consumer, we are going to pop wait for this elements. We are popping out everything from the queue. But if the queue is empty, the buffer is empty, pop wait simply suspends the coroutine, and that's it. That's what we need. We are handling backpressure implicitly. So let me show you a simple hello world example in a concurrent world. This is going to be a TCP echo server with buffer channels. So we start by creating a buffer channel for storing the accepted sockets. Next client is the limit how many connections we buffer concurrently. And this is going to be our acceptor coroutine. It waits for incoming connections using co-wait accept. Once a connection arrives, it pushes the socket into our buffer channel. And that's it. On the other hand, we have our echo coroutine task, which acts as a worker. It pulls sockets from the buffer channel with pop wait, reads data asynchronously, and writes back asynchronously. Notice how this is everything non-blocking here. So even though the coroutines appear sequentially, the underlying IO is fully asynchronous. And finally, we launch everything by using the all-of combiner. So one coroutine accept, one coroutine for accepting connections, and 4 coroutine handling clients concurrently. So by launching 4 echo coroutines, we can serve up to 4 clients simultaneously, which matches exactly the max client buffer size we defined earlier. So this is one solution for this TCP echo server problem. It has drawbacks and benefits. One of the benefits is that we are pre-allocating basically everything by starting this echo server, and therefore no dynamic allocation happens inside this example. But I think we can do better. And now we arrive to our next concept, which is the task groups. Task groups are one of the fundamental elements in structured concurrency. They are so special that they always have different names in different languages. Swift calls them task group, Rust task scope, Java structured task scope, Python, Trio nursery, and so on, always different names. If you take a look into this example, what we have here, we have a scheduler, which gives us parallel execution. We have our task, which does some async work and returns 42. So you can think of it just as a one independent unit of concurrent work, nothing more. Our goal is to place these tasks into a task group. The reason why we need to do that is structured concurrency. So with task group, we can simply achieve that, but a task group is more not just a simple container for results. It also defines a strict lifetime boundary. So no task may outlive the owner task group. So that makes the task group very, very important. So if one task belongs to the group takes the responsibility for it until the task finishes. So this is our producer, and we create a group there. And then we are going to start 10 tasks concurrently on the provided scheduler. That's great. And we are going to join this task group and wait for the entire group to complete. So once the join is finished, we know that all the tasks are done, and we can safely consume their results with group next. So this API is pretty similar to Swift. And this is not by accident. So the important thing is to notice here, one of the biggest difference is, although the task groups destructor also waits for unfinished task, but this is going to be a thread blocking wait. So the reason is why, because C++ has no support yet for co-wait in the destructors, and probably never will, but hope for the best. So in coroutine context, is it highly recommended to use the join explicitly? Because this makes this joining the group a non-blocking wait. And if we take a look now our hello world example, we have here a scheduler, and we have an echo. The echo routine reads from the socket and writes back, everything asynchronous, everything fine. And inside our acceptor, we have now our task group on line 2, so the acceptor waits for incoming connections and spawns each task for each client. So every time a new connection arrives, we are spawning a new task for this client to provide. So each client runs concurrently, and the scheduler handles everything, the execution in the background, does the voodoo magic. So this gives us structured concurrency. Tasks are tracked, and we can wait for them as a complete group. This particular version does not handle back pressure yet, what we did in a buffer channel example, but you can simply add it. We don't need to touch the group or the logic itself, just a very few changes. We are just extending. We introduce a semaphore with a fixed size 4. This is going to be the limit, how many connections are allowed to run concurrently. And before we spawning a new task, we are simply co-evaluating this semaphore. And and if the system is overloaded, the acceptor coroutine simply just suspends. And when the task finishes, this is the echo task finishes, it releases the semaphore slot, allowing the next connection to proceed. So now we basically achieve the same result as with buffer channel. So Swift task groups in tinycoro are inspired mostly by Swift, but there are also some differences. Swift task group is tightly bound to lexical scope that gives very strong safety guarantees, but also limits the flexibility. In C++, we don't really have an async scope in the same sense. That means a task group can be passed around as a pointer anyway, so we cannot prevent that. So this is on one side, this is great because this gives more control to the user, but it also introduces potential issues. For example, the task group, it is technically possible to call join or next from within a child task in the same group, which can lead to deadlocks immediately. Now you can ask me, are you sure this is the right this API design? This is everything correct now? But if we think about safety and what matters the most, when we take the safe languages, we often imagine something like this: that software development is just a comfortable drive. There is a car, there is a driver, and maybe a co-pilot nowadays. The car represents the language or the framework, and we are the driver. Hopefully we are behind the wheels, not the co-pilot, but this is another question. But anyway, however, the road is clear, the visibility is good, everything seems under control. That's what we imagine about software development. So this picture tempting to believe, that the car itself keeps us safe. The car, the language, is going to protect us from everything. But in reality, software development looks more like this, that we are driving in the upside down and no language will save us there. There's so many danger. So in the most important safety feature there is not the car anymore, not the language, it's a driver. So back to the topic. Yes, calling join from within a child task can deadlock, for sure. But this is not a subtle production bug. This is going to be a very loud logic error. So this kind of deadlocks will show up extremely early, mostly during development phase or testing. So we could try, on the other hand, we could try to prevent this by throwing an exception or adding some extra runtime checks. But in practice, those checks can be anyway bypassed. So instead, we make this mistake really, really obvious. So if you hit a deadlock here, this is going to be a very strong signal that your task structure is wrong. So now that we touched the topic safety, let me share some common pitfalls in the async world. By the way, if we are comparing languages to cars, I agree with some of you that C++ is more like a 600 horsepower Mustang with a manual gearbox. It's not the easiest car to drive, but it's definitely fun. So our first danger is the dangling reference. What we have here is a coroutine function which simply takes stud string as constref and simply prints it. Nothing unusual so far, right? And if we try to covate this task, in the first try we are safe because this is now everything under control. This is a temporary object, but we are covating it in the same line. So this temporary object will be destroyed at this semicolon, and therefore we outlive the coroutine execution. But what about this code? This is going to lead to undefined behavior immediately. The problem is here that const string reference can bound to R values, to temporaries. And this is a problem, because if we are creating this task, this temporary string is destroyed, and if we try to covate them, this is undefined behavior because the reference became a dangling reference. But what can we do to prevent that? So my suggestion would be in situations that if you can, try to pass everything by value. If you can afford, of course. If it's not too heavy to copy the object, because this is always safe. If we take those two examples, in both sides we are safe because we are copying the string into the coroutine frame, and therefore it doesn't really matter if there was a temporary. It's already inside the coroutine frame, and everything is fine. Here's a very similar issue, but this time with a member coroutine function. So we have foo, and this foo struct has a member coroutine get value, which depends on the member m_value. Our first example is safe. Although we are using a temporary foo class, we are invoking it immediately, the get value, and covating it at the same time, and therefore this foo will outlive this coroutine execution. That's fine. But what about this? This is not safe. This is going to lead to undefined behavior immediately, because the foo object is just a temporary and going to be destroyed after line 14. And if we try to covate this task, we are referring some dangling members which are not there anymore. So this is undefined behavior. But what about lambda functions? Lambda functions can become also coroutine, right? So in our case, we have now an immediately invoke lambda function. What we have here, we are co-returning the value which we are passing by in his capture. The problem here is that we are implicitly creating a lambda object. So if you are using the capture, you are creating a lambda object, and that object has a lifetime, which is also going to end after line 4. And if you try to correlate them, this task, the underlying lambda function is not there anymore. So task and the coroutine, the task and the underlying lambda function, they are not tightly bound. They can be separated. This is flexible, but could lead to some interesting behaviors. To solve this, we are doing pretty much the same. We have an immediately invoke lambda function with a value, but now in the second example, we are passing it as a parameter, not as a capture. And therefore, we are not creating a lambda object. Our lambda is just like a free function, which has one unique address in your entire program, and which you can reach from everywhere. And therefore, this is great. So this lambda has no lifetime. But now let me show you at the end some C++ coroutine libraries. So when I started looking into coroutines, I realized that there were already several excellent implementations after. So each of them solved the problem a little differently, and each of those has drawbacks and advantages, which is not a bad thing, I guess. So first is a cplusplus from Louis Baker. This library has a very nice API design. It provides low-level and flexible building blocks for coroutines, which makes it powerful, but it also expects a solid understanding from the user. Second is the Coral from the Hudson River Trading. It's a very high-quality implementation. It has a very well-designed cancellation model and structure task groups. They call them, I think, nursery. Another one is Fully from Meta. It's a very mature and production-proven implementation. They used at scale, but they come with heavier dependencies since they are part of the, let's say, larger Fully ecosystem. And last but not least, tinycoro, which is designed to be beginner-friendly with a very strong focus on usability and simplicity. It is just a header-only library, it has the pipeline has around 1,600 unit tests, I think, and we are running almost 40 different compiler setups there. So it's pretty well tested. It's not a toy project anymore or pet project like that. So it's much better to see these happy faces now, right? So I don't know if you remember, but I mentioned at the beginning that C++ had some kind of broken relationship with coroutines. That was not true. The relationship is not broken, they are just low level. So thanks for sticking with me until the end, and don't give up on C++ coroutines. They are definitely better than they look. Yeah, thank you. And I think we can now move together to the Q&A session. Thanks.